Okay, Chapter 6, Section 3, Integration by Parts. Okay, so far we've learned a lot about integrals. We can solve relatively straightforward integrals such as the integral of x to the power of 3 dx by using our power rule in reverse, our power rule for integrals. We know that when we take derivatives, we subtract 1 from the exponent, so we know that in order to find this integral, we add 1 to the exponent. So it has something to do with power 4. And then when we take the derivative, we know we have to bring the exponent out in front. So if we don't want that, we need to balance it out with a 1 over 3 plus 1, like that. Or that this is equal to 1/4 x to the 4th power. And then, of course, this represents a whole family of functions, plus c, a whole family of functions such that the derivative of this function equals to that, right? So this isn't part of it, but we can also check very easily, check that the derivative with respect to x of this function, 1/4 x to the 4th plus any constant c, the derivative of this is going to be equal to 1/4 times 4x to the power of 3 plus 0. The derivative of any constant number is 0. And then the 4 and the 1/4 will cancel, giving you exactly what we expected, x to the 3rd power. Right? Okay, so by now that's a pretty straightforward one. We could also maybe work with something like the derivative of 1 over x dx. That's also going to be a pretty straightforward one. If we remember our rules of differentiation, we know that the limit of x is a function such that its derivative will be 1 over x. We just have to be careful to qualify it because over here, when you see 1 over x, there's nothing nothing obvious that's stopping x from being a negative number. We could have 1 over -2, for instance. Nothing wrong with that. So there's nothing inherent about it that tells us that x can't be negative, but we know that the argument of a log function has to be positive. So we do have to qualify this by introducing an extra little thing here and making it the absolute value. So the absolute value of ln x equals to 1 over x plus c. So early on, we really just relied on our knowledge of derivatives to be able to find these integrals, these indefinite integrals. We were able to come up with a slightly more sophisticated way of finding integrals by using the substitution method, and that added to the number of things we could solve. So, for instance, we were able to solve integrals that look like this, about the integral of e to the 3x squared, and there's an extra, I don't know, let's make it a 5x out here, dx. Okay, so to solve this integral, what we want to do is use our u substitution. So we want to note that this guy up here, when I take its derivative, it's going to be something to the power of 1, and then there is something to the power of 1 here. So that'll make it useful for us. So we want to do the u substitution. Let's let u equal to 3x squared. Then the derivative with respect to x, ddx of the u equals to ddx of the 3x squared. That gives me du dx equals to 6x. And now du equals to 6x dx. So we almost have exactly our du. So I'm getting ready to do my substitution. So I'm going to scoot this over here. So now I'm almost ready to do my substitution. So I'm going to bring this over here and say that this is going to be equal to the integral. And I'm going to put the 5 out here. And I'm going to switch around the order. So this is e to the power of 3x squared. And then there's an x, and there's a dx, right? So I just moved around the order so I can still maintain that equal sign. And this is really close to my du. I just need that extra 6 right in here. right? This needed a constant of a 6. So I'm just going to toss it in there, an extra 6. That way it's exactly my du. Of course, I can't just go around tossing an extra 6 in there, so I got to balance it out by also dividing by 6. Or if you'd like, let's put some space here, I could just write it as a 1 over 6. So 1/6 times 6 equals 1, and there was still this extra 5 here. So I know I'll end up with a 5 divided by 6 out here. Okay, and now I'm ready to do my substitution. This right here is du, and this up here is my u. So now I know that this becomes 5 over 6 integral of e to the u du. And we know that e to the u is just e to the u, right? The indefinite integral of e to the u is just going to be e to the u. So this becomes 5 over 6 times e to the u plus a constant. And then we come back and replace the u back again with this, and we get 5 over 6 e to the power of 3x squared plus c. And that's our answer. So I'm going to copy the original indefinite integral as 5x e to the 3x squared dx. And that equals this guy. That would be our answer. Okay. And again, we can easily check. Nice thing about all these is we can easily check by taking the derivative of our answer, confirm that in fact it does equal to that. So let's check it right underneath here, see if it's really true. Check. All right, so then if it's true, that must mean that the derivative with respect to x of 5 over 6 e to the 3x squared plus a constant, the derivative of this should be equal to this. Okay, so this is equal to 5 over 6. The derivative of e to the 3x squared, well, that's going to be e to the 3x squared times, the chain rule says I got to multiply times the derivative of the exponent of this guy, the exponent, the inside function. It's x squared, which then gives me, oh, and the derivative of c is equal to 0, plus the derivative with respect to x of a constant. Well, that's just going to be 0. And now the derivative of this guy is just going to be 6x. So we end up with 5 over 6 e to the 3x squared times 6x. And now the 6's cancel, giving me 5x, right? Giving me exactly what I expected. 5x e to the 3x squared, right? Just as I had suspected. So it works out. Great, so we have the substitution rule, and that helps us solve a lot of stuff, but it doesn't help us solve everything, right? So we can refer back to kind of standard properties of derivatives or some common derivatives to be able to find some of these indefinite integrals, or we can use the substitution rule sometimes, but they don't solve everything. For instance, for all our knowledge and work and techniques, we don't know how to solve this seemingly simple integral, right? Something whose derivative equals ln x. Not sure. Don't confuse it with this one. This one's the other way around. Something whose derivative equals to 1 over x. Yeah, that's going to be ln x. The derivative of ln x equals to 1 over x. But we don't know, at least at this moment, we don't really know of a function whose derivative equals ln x. And the substitution rule doesn't really work here because there's only ln x. You know, what would you let your u be? You let u equal to x, and then you're just going to end up with ln of u du. But that doesn't really change anything. So we're kind of stuck. We need a new technique, a new method for solving these types of integrals. And that's where this section comes in. So we're going to develop a new technique called integration by parts. And integration by parts is a technique that's developed by thinking about our product rule. So let's go back to our product rule, see if you remember that. So if you recall, the product rule for derivatives is as follows. Let's say we have two functions, f of x times some other function g of x. And I want to find the derivative of the product of these two functions. So I want to find the derivative of the whole thing, d dx of the whole thing. Well, the product rule says that it's equal to the following pattern. We're going to take the derivative of, well, let me write it down this way. It's f of x g of x plus f of x g of x. Okay, so what we're going to do is we're going to take the derivative of one of them, the first one, say. So we're going to take d dx of the first function, leave the second function alone, plus now leave the first function alone, and then take the derivative with respect to x of the second function. Okay, so it's kind of a take turns kind of thing, and then add them in the middle. Right, so there's different ways of expressing the exact same thing. This little tick mark notation is also quite nice. So I'm going to do a little bit of a hybrid. Well, okay, so we can also write it this way. We could say if we have u times v, function u times function v, and I want to take the derivative of the entire thing, that would be, here I'm just gonna copy it down this way. U times v plus u times v. I'm going to put it in blue. So the derivative of the entire thing is equal to the derivative of the u, leave the v alone, plus leave the u alone, derivative of the v. Okay, so it's a neater way of writing it. They both mean the same thing. So I'm going to do a bit of a hybrid of the two. I'm just going to start off by writing it this way. Derivative with respect to x of, and then it's f of x times g of x equals, and then I'm going to use this style of notation with the function. So I'll say it's equal to f of x prime g of x times g of x plus now f of x times and then g prime of x. So a bit of a hybrid notation of the two. Okay, so what I want to do now is integrate both sides of the equal sign. So I'll have the integral of the derivative with respect to x of f of x times g of x dx, right? And that's where this entire thing here is the integrand, right? So kind of wrapping all of that around these two notations, meaning that I want to find the integral of both of those. Let's take that off, and in fact, we wrap it around this blue like that. Okay, so integrate that side, and then I want to integrate the other side as well. So the other side would be the integral of f prime of x times g of x dx plus the integral of f of x times g prime of x dx. Okay, so next, what I want to do is I want to take this entire value here and move it over to the other side. And I end up with the integral of dx of f of x times g of x d of x minus the integral of f prime of x times g of x dx equals to the integral of f of x times g prime of x dx. Okay, let me highlight some stuff since it might be easy to get lost. So this term is still right here. And then I took this term here, which I'm highlighting in yellow, and I subtracted it from both sides of the equal sign. So there it is. And then finally there's this term, right? So all it is, I took this green one and I subtracted it from both sides of the equal sign. So now, for space reasons, my equal sign has moved over here. Okay, let me remove this. Now we know that the integral of the derivative, these two operations undo each other. So this is just going to be equal to f of x times g of x. And of course we know that at this stage there would be a constant, right? So plus a constant. This is a function such that its derivative would be equal to that. Well, there would be an extra constant, but we'll leave it alone for now, and when we do an example, we'll see why it doesn't matter. Okay, next we have this minus the integral of this, and then all I'm going to do with this guy is just flip it around. That's all. So that shouldn't change the value, and this would be equal to g of x times f prime of x dx equals to this guy, integral of f of x times g prime of x dx. Okay, so once again, all I'm going to do is move things around a little bit just to make it fit the standard form of the presentation of integration by parts. I'm going to begin by moving everything from the left-hand side to the right and the right to the left. I'm just going to flip it around. So this statement right here is equivalent to saying that the integral of f of x g prime of x dx is equal to this minus that, which is going to be equal to f of x times g of x minus the integral of g of x f prime of x dx. And that's it. This is the formula for integration by parts. I know it doesn't look like much, but let's study it for a second. Let me zoom out. So we started off with the product rule, and by manipulating things a little bit and moving things around, we end up with this new formula. And what this formula is going to allow us to do is that if we start off with an integral that fits this form, it's some function f of x times some function g prime of x dx, then this formula tells us that we can exchange that one integral into a product of these two functions minus this integral. And you're like, well, what's the point? Well, hopefully, the point is that this integral here might be really hard. Now, this integral right here might be hard to find. And you're going to exchange it for a multiplication of functions times an integral that hopefully is less hard. I mean, I'm not going to lie to you and tell you that it's going to be easy. It might still be challenging, but we'll say less hard. At least that's the goal, to exchange one really hard integral for a product of functions minus an integral that's a little less hard, something that's manageable, doable, or can fit some other pattern that's useful for us. That's the goal of integration by parts. There's another way that this is often presented, so let's explore that. So another common way that this is often presented is to do the following substitution. If we let u equal to some function f of x, then we know that the derivative of u is going to be, with respect to x, dx of u will be equal to ddx of f of x, which means that du dx will be equal to, let's call it f prime of x. And then we can multiply both sides of the equal sign by dx. Dx on this side, dx on that side, cancels out there. So we end up with du equals to f prime of x dx. Good. And then v, so we're going to have the following. Let's let v equal to, okay, so let's let v equal to a function g of x. And then we do the same thing, where if we take the derivative with respect to x, ddx of v, we'll end up with ddx of g of x, which gives us that dv over dx equals to g prime of x. And so dv is going to be equal to g prime of x dx. Okay, and so now we have everything we need to make substitutions here. So let me highlight. Let's see, we have u equals to f of x. We have v equals to g of x. We have du equals to f prime of x dx. And then we have, I don't like purple, let's go with orange. We have dv equals to g prime of x dx. So g prime of x dx is this term right here. So we're going to take that guy right there and we're going to replace it with a dv. Good. And then f prime of x dx, that's this thing right here, f prime of x dx. We're going to take du and replace that part right there. Then we have v equals to g of x, and v equals to g of x there. And finally, we have that u equals to f of x, so that would be this u there and this u there. Okay, so we end up with a u here, a u there, and a u there, and then a v here. U there, u there. Okay, let's go with v here. So then this is going to be a v, and this is going to be a v. And this is dv, and this one over here is du. This green one, right? Du. Okay, colorful enough for you? So let's resubstitute the whole thing. And so we'd say that, coming back to here, let's get rid of all them colors. There's going to be the integral of, that's going to be u times dv equals to u times v minus the integral of b du, right? And then that provides us the other way that this is often referred to. Box that up. Good. All right, so it's either this way or that way, and let me just get rid of all those colors everywhere and just get back to the way it was. There. So either this way or this way, same thing. Gives you the method of integration by parts. And this little part in here is actually kind of useful. Once we actually do an example, I'll show you how this helps us figure it out. Okay, so again, at this moment, perhaps it's a little mysterious why this is useful. But let's do an example and we'll see how we can implement this. And the key to all of it really is to figure out what your value of u and what your value of dv should be. Why? Because this is where you're going to get started. We're going to be given an integral that fits this form, and we're going to have to make a choice to substitute or assign the value of u and assign the value of dv. And from that, we have to unravel the other ones. So in other words, in practice, we're going to start off by assigning a value of u. So we're going to say let u equal to something, right? So that's something we're going to do right there, based on just this integral that's provided for us. And then off to sort of on the side here, we're going to figure out this one, except we start off here, we're going to be given some dv equals to, and we need to figure out what that is. So there will be some sort of value that we need to figure out. That's what goes here. And then we can find the other ones. In this direction, we're going to have to take a derivative. And that'll help us find our du. And then in this direction, we're going to have to take an integral, so that we can find our value. So taking the derivative, it'll help us find our du. And finding an integral will help us find v. And so by having this little square like this, we're able to state that the original integral is equal to the multiplication of the u times the v minus the integral of the v times the du. So the order of this little square here will be really important. The multiplication of these two things will give you this term here. And that's going to be equal to the product of these two things, this one and that one, minus the integral of these two things. Right? So it's this sort of a Z shape that happens. Okay, all right, so let's just get to an example and hopefully that'll make more sense then. So with this in mind, let's go ahead and try an example out. Okay, so let's say we're asked to find this integral, x times ln x dx, the integral of x ln x dx. Keep in mind that if we're going to use the integration by parts, we need to choose the appropriate value of u and the appropriate value of v or dv. So I'm going to write down the integration by parts over here on the side. Integration by parts, right? And the easiest one to remember is that the integral of u dv equals to u v minus the integral of v du. Okay, so keeping that in mind, we're starting off with this one. So this has to be some u dv, right? So we have to assign which part would be the u and which part would be the dv. Then we need to figure out what u is, what v is, what du is, so that we can, put together the rest of this. So I'm going to create that little square underneath it. So I'm going to assign u, and this is really the hardest part. How do you assign things? Well, typically what you want to do is assign u something so that its derivative is easier than what you started with. But that's just kind of a general idea. That's not always true. So it just takes a little bit of experience. So I'm just going to assign u equal to ln x, and the rest of it is going to be assigned to dv off to the side over here. So dv then is going to be equal to the x and the dx. So it's x dx. Good. Okay, so now I'm going to take a derivative going this way, so that I'm going to find d dx of the u equals to d dx of the ln of x. That's just going to give me du dx equals to, and the derivative of ln x is equal to 1 over x. And now du is equal to 1 over x dx. Good. So I have this guy, my u, and I just discovered my du, this guy. All right, almost there. Now I already have my dv, it's this guy. Now I have to figure out v. To figure out v, I got to integrate both sides. So I'm going to take the integral of dv. Now if there's nothing there, by default there's a 1. So that's just going to be the integral of 1 dv is equal to the integral of x dx. And the integral of 1 dv is just going to be equal to v equals to, and then the integral of this one is going to be equal to 1/2 x to the second power. Don't worry about constants. Constants don't matter here. We'll get the same answer anyway. So now we have everything we need to fill in this little formula. So let's fill in that formula. The formula is that the integral of x ln x dx is going to be equal to, and I'm going to follow this z. That's why I'm very careful about creating this square the way I do, because it's going to be that the product of these two is equal to the product of these two minus the integral of these two, right? It's this z. Now, you don't have to do this box, but then people get very confused. A very common source of mistakes is people don't properly substitute or apply this integration by parts. So just be really careful about how you do it and meticulous in the way you apply it. So the multiplication of these two, that's this. This is my, well, you know what? I can, just to make it look pretty, I'm just going to flip it around a little and say that it's ln x and then x dx, like this. So here is my this, I assign this to be my dv, and I assign this to be my u. So this is u dv. u dv. Good. Equals to, and then it's going to be u times v. So that'll be equal to ln x times 1/2 x squared. That's my u dv. I'm sorry, u times v. U times v. My u times my v minus, and now it's the integral of these two. So it's going to be equal to 1/2 x to the second power times 1/x dx. Good. And so now this is going to be my du, and this is my v. Good. So I've properly exchanged everything here. U dv, the integral of u dv is equal to u times v minus the integral of v du. Good. Okay, so if things worked out nicely, it should be that this is something easier to integrate compared to that. Good. So this is just going to be, let's just simplify it a little bit. This is going to be 1/2. I'm just going to flip it around and say it's 1/2 times x squared ln of x minus, and then just simplifying this a little bit, I'm going to pull out the 1/2 integral of, and now one of these reduces with that guy to give you just x dx, and it does look a little easier. Good. So then this is going to be equal to 1/2 x squared times ln x minus 1/2, and the integral of x is just going to be equal to 1/2 x squared. So we multiply those two together. And so we end up with 1/2 x squared ln x minus 1/4 x squared. And we're almost done. We just have to now throw in that constant, plus a constant. So earlier, when we were looking at the formula, I was constantly ignoring all those constants, and that's because, well, you get a constant from here, you get a constant from there, and so at the end of the day, all those constants can kind of add up together, and so you end up with some constant at the end, right? I don't know if I said that properly. So, you know, technically at this point, there would have been a constant here. Let's add it here. When I did this, there would have been some plus constant here, right? And then that means there would have been a constant there. And then that kind of brought down, and there'd be some plus constant there. And then, well, okay, so there's another constant here. Let's put it in some other constant there from this, finding this integral. Okay, but then the red constant plus the green constant is just some constant. It gives you the black constant, right? So it doesn't really matter. Ultimately, there's a constant at the end. That's all that really matters. And so we don't really need to keep track of them. All right, so that means that this is the integral of, and then putting it back the way it was, just flipping these around, ln x dx is equal to this. So we're done. That's how we solve that integral. Luckily, we know that when we find integrals like this, we can easily check them. So let me zoom out. There it is. So we start out with this guy, we did integration by parts, and we end up with this answer. And now we can check it. So I'm going to come back over here and check it. Check. If in fact it's true that this is the derivative, it must be the case, that this is the integral, then it must be the case that the derivative of this function equals to that guy. So let's check it, see if it's true. Is it true? Derivative with respect to x. Okay, let me zoom in here. Is it true that the derivative of all this simplifies to just x ln x? All right, so for this first term, we're going to have a product rule. So this is equal to d dx of the 1/2 x squared ln x minus d dx of, and we know that the derivative of a constant is going to be 0. So I already know there's a plus 0 out there that I can just ignore. Okay, here I'm going to need the product rule, so I can pull out that 1/2. So it'll be 1/2 times, and it'll be x squared ln x plus x squared ln x. And I'm going to take turns taking derivatives. So I'm going to take a derivative of this one, leave that one alone. Now leave that one alone, take the derivative of that one. Good. Next, I'm going to minus 1/4. Oh, this minus, make space here. I got to end this bracket. The 1/2 applied to both of them, so that applies there. Minus, and then there's a 1/4, and the derivative of x squared is just going to be 2 times x to the power of 1. Okay, so then this becomes 1/2. Now the derivative of the first one is going to be equal to 2x to the power of 1 ln x plus 1/2 and then x squared. And the derivative of ln x is going to be equal to 1 over x. Right, this 1/2 comes from distributing the 1/2 times 1/2 here. So 1/2 here and 1/2 there. That's how we get that. Minus, and then out here we had a minus. This is going to be 1/2 x. Okay, now a bunch of stuff will reduce. This reduces with that, and this reduces with that to just give me a 1. So it's just going to be plus 1/2 x. And so I'll end up with x ln x plus 1/2 x minus 1/2 x. And now those two cancel. These two cancel, giving me exactly what I had expected. It equals to x ln x. Okay, so we've confirmed that this is a function, this crazy looking thing here is a function such that its derivative equals to x ln x. Okay, so we've confirmed that this is a function such that the derivative of that function equals to x ln x. So that confirms that this indefinite integral is in fact correct. Okay, so just be careful with the process. Be very clear about how you define your u, how you define your dv. I strongly recommend that you create this little box. And remember, we assign our u, we assign our dv. That's the beginning of the integral. That's the left side of this integration by parts formula. And then we take derivatives this way, we take integrals this way, and then we use this z to figure out our statement, our equation. All right, let's try another one. All right, let's say we were asked to integrate this, the integral of x squared times e to the 2x plus 1 dx. Okay, so let's do this by integration by parts. So let's write down our little formula for integration by parts off to the side. So we know that by parts, it's going to be the integral of u dv equals to u times v minus the integral of v du. Good. So that is something you're going to have to memorize. Well, not in this class since you have your notes, but okay, so the whole goal here is to figure out what should be your u, what should be your dv. And again, that's not always easy. If I decide to let my u equal to the e to the 2x plus 1, the derivative is going to be easy. No problem. It's going to be the du equals to e to the 2x plus 1 times an extra 2 in there, dx. Easy. But notice what happens with the dv. If I let dv equal to the x squared dx, then when I integrate both sides, I'm going to have to find the integral of that, then I'm going to go up by 1 power. I'm going to end up with x to the 3rd power times 1/3. And that's just getting more complicated. I'm not making it simpler, I'm making it more complicated. So that's not the way to go. If you start going that way and you end up with something that's more complicated than what you started with, that might be a clue to stop, come back, and maybe choose a different value of u and dv. A lot of that just comes with experience. So let's let u equal to the x squared, because I know that when I take derivatives, the power will go down. At least we're heading in the right direction. And so I'm going to let the dv equal to the rest of it, which is e to the 2x plus 1 dx. Okay, so going this way, I take derivatives. So I'm going to take the derivative with respect to x on the u, the derivative with respect to x on the x squared. So that'll be du dx equals to 2x. And so that means that du equals to 2x dx. Good. So I have the u, and I just discovered the du. Almost there. So now I'm going to integrate both sides of this. So I'm going to copy it down. So it'll be dv equals to e to the 2x plus 1 dx. I'm going to integrate that side and integrate this side. And if there's nothing there, well, then there's like a little 1 there. All right, so on the left-hand side, I'm just going to get v. V equals 2. And now this should be an easy integral. This is just going to be equal to 2e to the 2x plus 1. And then by the chain rule, I know that when I take the derivative of this function, I'll still have times the derivative of 2x plus 1, which would be an extra term of 2. So I know I have to fix it by adding a 1/2. Right? The derivative of this is going to be equal to that. So I have my v. So I have my dv there, and now I have my v there. Okay, so now I very carefully replace those values into this formula. So the product of these two, so that's my u and my dv. That's the left side of this integral. Integral of u dv, that's these two, is equal to the multiplication of these two functions minus the integral of these two functions. So let me copy it again. So this is the integral of x squared e to the 2x plus 1 dx. It's going to be equal to x squared times 1/2 e to the 2x plus 1 minus the integral of 1/2 e to the 2x plus 1 times 2x dx. Good. So that's where this guy is my u. All of this was my dv. This guy is again my u. All of this is my v. And then this guy is my v. And this guy over here is my du. Right, so carefully replacing those values there in my integration by parts formula. Okay, let's try and simplify this a little bit. We see that this 1/2 and this 2 simplify. And so I end up with, just rewriting the order of this, I'm just going to say it's equal to 1/2 x squared e to the 2x plus 1 minus the integral of, and I guess I'll just switch those two around a little bit and say that that's x e to the 2x plus 1 dx. Still not a very easy integral to solve, but we're in the right direction. We're headed in the right direction. This has power 1. It's better than that one that had power 2. So we managed to reduce it by 1 power. So what we're going to do is repeat the process again and use integration by parts again on this portion of it, just this integral. So I'm going to come right down here, and I'm going to assign the same values again. I'm going to assign a new integration by parts problem where this will be u equals to x, and my dv equals to e to the 2x plus 1 dx. So now when I take the derivative, ddx of the u equals to ddx of the x. That gives me du dx equals to just 1. So my du equals to my dx. And on the other side, when I integrate, 1 times dv equals to the integral of e to the 2x plus 1 dx. this turns out to just be v equals to, and then this side we get the same answer as before, e to the 2x plus 1, and we have to fix it by putting an extra 1/2 constant out in front. And so again, we have all our values we need, that guy, this guy, this guy, and this guy. So we have all 4 parts, and so the multiplication of these two is equal to the product of these two minus the integral of these two. It's a little crooked, but there's my z. So I'm going to come down here, I'm going to copy all of this down and say that this, coming back from there, is equal to 1/2 x squared e to the 2x plus 1 minus, I'll put a giant bracket here. Now it's the multiplication of these two, so it'll be x times 1/2 e to the 2x plus 1 minus the integral of these two, which will be equal to 1/2 e to the 2x plus 1 dx. Good. Now we have to be careful with this subtraction. We got to distribute it. So we got to distribute, this minus goes there, distributing it there, and then this minus also distributes there. And this is a pretty simple integral to find. So let's copy that. Erase this. So this is going to be equal to 1/2 x squared e to the 2x plus 1 minus, and then this is going to be 1/2 x e to the 2x plus 1 minus, and then plus this answer, so it'll be a 1/2 from there. And now this guy is going to be e to the 2x plus 1, and then it's going to have another term of 1/2 out in front, right? So maybe it's just to highlight it, this is the one that goes there, just brought it out front. And now the integral of e to the 2x plus 1, it's going to have another term of 1/2, right? The derivative of just this part right in here is going to be equal to this. And so we're basically done. So let me zoom out a little bit more. This is just going to be 1/2, so this is going to be equal to 1/2 x squared e to the 2x plus 1 minus 1/2 x e to the 2x plus 1 plus 1/4 e to the 2x plus 1. And of course, we always have a plus a constant. Good, so let me zoom out. Okay, so we started with this integral, the integral of x squared e to the 2x plus 1 dx. We applied our integration by parts once, and we end up with this statement here. And then we applied our integration by parts again to this integral. Be careful to bring down this initial part right here. Right, so don't forget to bring this part here. This part here comes down there. Minus, from there, that minus is that minus. And now this whole integral, we do integration by parts once again. Set it up. Don't forget to distribute that minus properly. And then simplify. So our initial integral, the one we were really starting with, is equal, here it is equal to that, which equals to that, all the way down. So our final answer is this guy. So I'm going to box it up. The integral of x squared e to the 2x plus 1 dx is equal to this. Of course, we can also factor out a 1/2 and then e to the 2x plus 1. They all share in common, so I'll put or. You could say that the integral of x squared e to the 2x plus 1 dx is equal to, let's factor out the 1/2 e to the 2x plus 1. And what remains is an x squared in the first term. So x squared from there remains, minus x from there, and plus 1/2 from here, plus c. So there's another way of expressing the exact same thing. Okay, so hopefully what we've learned from this is that sometimes you gotta, if you don't succeed, try again. You might have to repeat the integration by parts process more than once. Twice the fun. Okay, so let's check if in fact this is true. I'm gonna zoom into here and confirm using this version of it. Is it true that when I take the derivative of the right side, it gives me the left side? That's what we want to check. So let's check. Check. Is it true that the derivative with respect to x on the 1/2 e to the 2x plus 1 times x squared minus x plus 1/2 plus c, the derivative of all that just equals x squared e to the 2x plus 1. Okay, so noticing that there is a multiplication there, I have a product rule. So this is going to be equal to the derivative with respect to x on the e to the, well, let's take out the 2. Sorry, let's take out the 1/2. So it'll be equal to 1/2 out here times, and then I'll take turns with these two, so it'll be the derivative with respect to x on the e to the 2x plus 1, figure out what that is, times x squared minus x plus 1/2, plus, and now we'll leave the e to the 2x plus 1 alone, times the derivative with respect to x on the polynomial, is x squared minus x plus 1/2. And then the derivative of c is equal to 0, so there's a plus 0 out there we can just ignore. Okay, so this will be 1/2 here times, and now the derivative of this one is just going to be equal to e to the 2x plus 1 times the derivative of the exponent gives you an extra 2 times x squared minus x plus 1/2 plus, and now this becomes e to the 2x plus 1 times the derivative of that gives you 2x minus 1 and 0. Okay, distributing this 1/2 then gives me e to the 2x plus 1, and then 1/2 times 2 cancel out. We still have this x squared minus x plus 1/2 plus, and then distributing, we end up with 1/2 times e to the 2x plus 1 times 2x minus 1/2 e to the 2x plus 1. Good. So distributing this 1/2, I'll highlight it, this 1/2 gets distributed. So it canceled out with this 2 in this term. And then when I distribute it to this, I end up with a 1/2 there and a 1/2 there as I distribute 1/2 e to the 2x to this term and this term. That's how we get that. And now, distributing, I get e to the 2x plus 1 times x squared, so let's leave that x squared in there, minus x e to the 2x plus 1 plus 1/2 e to the 2x plus 1. And then this 1/2 and this 2 cancel to give me a plus x e to the 2x plus 1. And then minus 1/2 e to the 2x plus 1. Okay, so now this term, 1/2 e to the 2x plus 1, cancels with this term. And then x e to the 2x plus 1, that term will cancel with this term. this term and this term cancel. And so indeed we get exactly what we expected. The derivative of this function on the right is equal to this right here. Right, so we get what we expected. This whole thing equals to just x squared e to the 2x plus 1. Okay, so we've confirmed it. When we take the derivative on the right-hand side of this statement, the derivative of this equals to that. So we've confirmed that this integral is in fact correct. All right, so here are the exercises from 6.3. We've done lots of indefinite integrals so far, hopefully enough to get you, to a point where you can do your homework. But let's try one of the definite integrals. So let's try number 58. We'll see how they connect. Okay, let's say we're asked to find this definite integral, the integral from 1 to 2 on ln x e to the x power dx. Okay, so remember the connection between definite integrals and indefinite integrals. An indefinite integral is an antiderivative, right? It's the reverse of taking a derivative. And we need that because thanks to the fundamental theorem of calculus part 2, if we can rewrite this as the derivative of some function, then it'll make it very easy to figure out this integral, right? In other words, our goal is to find some function f of x, such that the derivative with respect to x of that function f of x is equal to the ln of x e to the x, right? Because then I can come back over here and say, okay, well, the integral from 1 to 2, the ln x e to the x, that's going to be equal to the derivative with respect to x on that function, dx, right? Since obviously if I can find a function whose derivative equals to that, then the derivative of that function equals to that part right in there, right? And now that I have an integral right next to a derivative, thanks to the fundamental theorem of calculus, we know that these two would undo each other, and the result would be capital F of x evaluated from 1 to 2, or just capital F of 2 minus F of 1. Okay, so our goal then is going to be to find that function, right? Find a function whose derivative equals to this. Well, that's exactly what this notation refers to. Find the indefinite integral of ln of x e to the x dx, right? So that's the connection between these two. Here we interpreted this as an area question. The area between this function and the x-axis, between x goes from 1, x goes to 2, whereas this is an antiderivative. Okay, so now let's work on this. When we can find that capital function f of x, we can come back over here and find this, this definite integral. So how do we find this guy? Let's scoot over here. So let's use the method of integration by parts. So let me write down the formula. The formula is the integral of u dv equals to u times v minus the integral of v du. Okay, so there's my formula. So now it all comes down to choosing the appropriate value of u. So this one could be a little tricky, but there really isn't much choice, because if I let my v, right, so I have to get u equal to this, ln of x e to the x. Right, I have to set it up as a multiplication, so I can't separate the argument of this ln function. So that just leaves me another option of dv must be equal to dx. Right, there really isn't much choice other than this, right? So it would be wrong. A very common mistake is for people to say that it's equal to lx and then the dv equals to e to the x dx. Right, we can't separate those because this entire thing here is inside the log function. It's an argument of the log function. So you can't separate it like that, right? So this is not allowed. Right? This is not true. You can't separate them like that. The other thing you could do is make the whole thing dv, dv equal to ln of x e to the x dx. And then I guess u would just be a 1. So then the derivative would be 0, and then it's just ugly, right? And then you got to integrate this, and then the integral of ln, well, that's ugly. Well, that's in fact that guy. So, we haven't accomplished anything. Okay, so hopefully that convinces you that there really isn't any other choice. We have to do it this way. And let's see if it helps. The other nice thing is that we know how to take the derivative of an ln function. That's easy. If I had put the ln over there, I'd have to be integrating ln. Okay, so now we take derivatives in this direction. So it'll be the derivative with respect to x on the u is equal to the derivative with respect to x on the ln of x e to the x. And now this would be du dx equals to, and now remember the derivative of the log function is going to be to put it all underneath 1, x e to the x, times, the chain rule says now we've got to multiply times the derivative of the inside part, which is x e to the x. And now that in itself is going to be a product rule. So we kind of take turns taking derivatives. This will be du dx is equal to 1 over x e to the x times, and then the derivative of x is just going to be 1 times e to the x, plus x, and then the derivative of e to the x is just e to the x, like that. So that means that du is equal to e to the x plus x e to the x divided by x e to the x times dx. Okay, we come over to the other side. I'm just going to make some space. So then that means that the dv was equal to the dx. So we're going to integrate the left side. dv equals to the integral dx, right? If there's nothing there, by default, just put a little 1 there. So that just means that v equals to x is the result. And so now we have our box, I guess. So just to make it like a nicer box, I'm just going to scoot that down here. And here they are. We have our u here. We have our du down here. We have our dv is this, and we have our v is this, right? Don't forget that red z. These two are this one. The integral of u dv is equal to the multiplication of this function times that function minus the integral of this times that, right? It's that z value. Okay, so let's substitute it in. Zoom out a little bit. So I'll get that the original integral, the integral of ln x e to the x dx is equal to the multiplication of those two, which would be x times ln x e to the x minus the integral of these two, which would be equal to x times this ugly thing, e to the x plus x e to the x divided by x e to the x dx. Good. And then luckily these guys simplify. This cancels with that. And so we get x ln x e to the x minus the integral of, and then this turns into a 1. We have an e to the x over e to the x plus, and then these guys also cancel, so we just end up with 1 plus x. What's that? 1 plus x dx, and that's a simple integral. This would be x ln x e to the x minus, now be careful with the subtraction, with this subtraction sign it applies to the whole thing, so this becomes x plus 1/2 x squared plus some constant. Good. So we got our answer. This is x ln of x e to the x minus x minus 1/2 x squared plus some constant. Let me just copy this guy down. Integral of ln of x e to the x dx is equal to this. Good. Now let's check to make sure this is true. So if it's in fact true that we did a good job, it must be the case that the derivative of this function equals to that one. So let's check it. Is it true that the derivative with respect to x on x ln of x e to the x minus 1/2 x squared plus c, does it really give you just that guy right there? Okay, so we have a product rule for the first derivative, product rule. So let's deal with that. The derivative of x is just going to be 1 times this guy, ln of x e to the x, plus, now leave the x alone, and the derivative of this is going to be equal to 1 over x e to the x, times, the chain rule says I got to figure out the derivative of the inside part. So that'll be, the derivative of the inside part is going to be equal to 1 times e to the x plus x e to the x. Good. Minus 1 minus 1/2 2 times x. And then the derivative of the constant, well, that's just 0. And now things simplify quite nicely. Those guys cancel. This guy reduces with that guy. And so we end up with ln of x e to the x. And then we end up with plus, and now when I distribute this, well, I'll do one more step, e to the x times, and then we end up with e to the x plus x e to the x minus 1 minus x. And then when I distribute this 1 over e to the x, we end up with ln of x e to the x plus 1 plus x minus 1 minus x. Those guys will reduce, these guys cancel, and these guys cancel, and giving me exactly what I expected, that the derivative of this function equals to this. Good. So we have a capital F of x. We found it. We found a function whose derivative equals to this. So let's go back to our original question, the definite integral. Okay, armed with all that knowledge now, let's go back to the original definite integral way over here that they asked us to find. And now we found this capital F. We found a function whose derivative is equal to ln of x e to the x. So we know that we can rewrite this function this way. So the integral from 1 to 2 on ln of x e to the x dx is equal to the capital function, which is, as we saw, was equal to x ln of x e to the x minus x minus 1/2 x squared, and all of that gets evaluated from 1 to 2. So we're going to evaluate it this way. This is going to be blank ln of blank e to the blank minus blank minus 1/2 blank squared, and then we're going to have a minus, and then repeat the whole thing, blank ln of blank e to the blank. So, if you run out of space, nice little notation thing is just to put a like an indentation, little space there, minus, and then blank ln of blank e to the blank, that'll buy you a little bit of space, minus blank minus 1/2 blank squared. Okay, so it's going to be this function here, evaluated at 2, copied exactly the way that goes there, so let's put a 2 there. So it's going to be 2 ln of 2 e to the 2 power minus 2 minus 1/2 2 squared. That's all them evaluating with 2. Minus, and now it's this entire function here, all of it evaluated at 1. So let's put a 1 there. So it's 1 times e to the 1 times 1, times e to the 1 power, minus 1 minus 1/2 1 squared. Good. Okay, so that should take care of everything. Now we just try and simplify it as best we can. So this is going to be equal to 2 ln of 2 e to the 2 power minus 2 minus, so that's going to be 4 divided by, that's just going to be minus 2, 1/2 of 4, minus, and now this is going to be 1 times, this is just going to be 1, right? So 1 times ln, well, that's just the ln, and now ln of 1 times e, well, that's just going to be ln of e, and ln of e is just 1, so that's just going to be minus 1 plus 1 when I distribute that minus, and then minus becomes plus whatever that is, and well, 1 squared is just 1, so that's just going to be plus 1/2. Okay, well, that's ugly. That's going to be minus 2, minus 4, minus 5, back to minus 4, plus 1/2. Minus 4 plus 1/2 is minus 3.5 as a mixed number. So this is minus 3.5 as a mixed number. And then this is a 2 ln of 2e to the 2nd power. Not be simplified in any way. When we have a multiplication here, we can rewrite it as an addition. So this is equal to 2 times, and this is ln of 2 plus ln of e to the 2nd power minus, and then as a mixed number it was 3.5, a negative 3.5, but then we can rewrite it as a fraction as 6/7/2. Good. Ln of 2 can't really be simplified, but ln of e to the 2nd power, that's just going to be equal to 2. So this is going to be equal to 2 ln of 2 plus 2 times 2 minus 7/2. I should have left it as a 3.5. Would have been easier to think about it that way. But at any rate, so then this just becomes 2 ln of 2, and then 4 minus 3.5. 4 minus 3.5 is just 1/2. So plus 1/2. So there's our answer. The integral from 1 to 2, come back up here, integral from 1 to 2 on ln of x e to the x dx is equal to this guy. Okay, so that's a fantastic exact answer. But then we can approximate it using our calculator. So let's get our calculator out and get a decimal approximation for this. Here, let's come back over here. Okay, so it's going to be 2 times ln 2, 2 times ln of 2 plus 0.5. And we get that, 1.863. Let's round to 4 decimal places, 8863. So this is approximately equal to, so the integral from 1 to 2 on ln of x e to the x dx is approximately equal to 1.8863. Approximately, rounded to 4 decimal places. So there's another good answer. And we can use technology again to help us confirm that that's in fact the right answer. Remember that when these little limits of integration are not there, that's a definite, an indefinite integral. Indefinite integrals are these guys, right? This is a statement that says find the antiderivative. Find a function whose derivative equals to this, and we found it. Here it is. It's this one. On the other hand, when we're asked to find a definite integral like this, we can interpret this as an area on a graph. So let's use Desmos to graph this and then find the area that is between this function, the x-axis, and the values x equals to 1, x equals to 2, keeping in mind that any area below the x-axis is considered to be negative. So let's graph it. Okay, so here's my function, f of x equals to ln x e to the x. That's this guy right here. And if I want to find the area between 1 and 2, that would be this result right here. Area between 1 and 2. So below the function f of x equal to ln x e to the x, above the x-axis, and then trapped between the vertical lines x equals to 1 and x equals to 2. That's the area I want right in there. And then here on Desmos, I can just type in the integral like this, the definite integral, dx, and it gives me the answer, 1.8863, exactly what we got. Right, so this just helps us confirm that that's in fact the correct answer. We found that area. That area is equal to this answer right here. Right, and that matched our answer. Okay, so then this right here, this curvature right there, is the function ln of x e to the x, and the integral from 1 to 2 means we found this area in green, and we found that area in green to have the area is equal to approximately 1.8863. Okay, so hopefully that should be enough to help you complete your homework. Please try the homework out and come by my office hours if you have any questions.